Section 8.3, graphing general rational functions. Kind of tagging on to what we were starting with yesterday when we introduced a simple rational function, or we introduced one that had some vertical changes occurring and horizontal translation occurring with our asymptotes. So now we're going to expand upon that. We're going to go back and focus in on specifically some horizontal asymptotes, when we, how do we determine what the horizontal asymptote, but also introducing too this oblique asymptote as a topic of discussion, and also the concept of where am I going to find the x-intercepts in these rational functions. So remember, as a review, rational functions are two polynomials that are dividing by one another, and those polynomials may be of varying degree, and the degree of the polynomials help us determine what our horizontal asymptote is. So here we have the three rules that we talked about yesterday. Rule number one, what happens when the degree of your numerator is smaller than the degree of your denominator? We said that that is the case where y equals 0 is our horizontal asymptote. Rule number two, when our degrees of the top and the bottom are the same, we introduced the fact that I can use leading coefficients and determine the horizontal asymptote from the quotient of those leading coefficients. And then this third rule we mentioned, but we haven't done anything with it. We just said yesterday that it meant there are no horizontal asymptotes, but we did not take a look at the oblique asymptote or slant asymptote that does result from these types of rational functions. And that's what we're just going to look at today, not again doing much with it other than introducing it. All right, so those are our three conditions. And here we have a couple examples given each of those. So yesterday we talked about first things, and first things were find vertical asymptotes. So we go after vertical asymptotes in the denominator, x squared plus 2 equals 0, x squared equals negative 2, x equals plus or minus I root 2, and those are not real. And because of that, we have no vertical asymptotes. And anytime I've got in the denominator, in this case a binomial of even degree plus a constant, that's going to be my case where I don't have any vertical asymptotes down there. What about the horizontal asymptote? So horizontal asymptote, we already know that the degree on the top is a constant, and the degree on the bottom is 2. So we have a situation where automatically horizontal asymptote is y equals 0. Because of this, where m and n represent the numerator's degree and the denominator's degree. So horizontal asymptote y equals 0, we'll put that in. And then now we're ready to, next thing we would typically do is look for x-intercepts. Now that's new for us. We haven't talked about that as of yet. And where I find the x-intercepts is up in the numerator. And like we do with the denominator, we set the denominator equal to 0 to find vertical asymptotes. We set the numerator equal to 0 to find horizontal asymptotes. However, in this problem, our numerator is a constant. So there is no variable, so that means there are no x-intercepts for this example here. So now we're ready to just plug in some values and test. So when we plug in our table values here, we normally would have looked at the vertical asymptote and decided to go test points to the left and right. Well, now there is no vertical asymptote, so we're going to have to make sure we're testing plenty of points to see the shape. In this case, we'll test some negatives, we'll test x equals 0, and we'll test some positives. So I'm going to just plug in some numbers here, negative 5, negative 1, 0, 1, and 5. Plugging these in, negative 5 squared is 25, 25 plus 2 is 27, so we get negative 2 27ths there. Negative 1 squared is 1, 1 plus 2 is 3, negative 2 thirds. For 0, we get negative 2 over 2, which is negative 1. For 1, we get back to negative 2/3. And for 5, we get back to negative 2/27. So, real different looking graph here. Negative 5, negative 2/27, we're writing right next to that horizontal asymptote. And then we punch out a little bit with the 2/3 on either side, and then we get back to that horizontal asymptote again. So this is like a valley looking graph. There it is right there. A little unique, we haven't seen this before. Just for discussion, what about the domains of these graphs? For this one in particular, well, if I go both directions forever, my x's will be all reals. And my range for this graph, well, the lowest value, the minimum value is negative 1. Maximum value is less than 0. So here I have an interval. I'm going to be less than 0, but greater than or equal to negative 1 for the range of that. Let's try another one. So, again, this is your practice place. Go back and review and then try this and turn it on and see how, turn the video back on and see how you did. So, verticals. None. Because the fact is that I've got imaginary values of x in the denominator. Everything works down there. I don't produce a 0 in the denominator, so there's no vertical asymptote. Horizontal. The degrees are smaller on the top than the bottom. And x-intercepts. Once again, none, because I don't have any x values in the numerator. Then we test our points. I'm going to test the same ones we just did. Negative 5 squared, 25 plus 1 is 26, so you get 3 over 26, and then put a 1 in there, you get a 3 over 2. 0 gives me a 3, 3 over 2, 3 over 26. So I'm going to get something that looks like so. And there's your graph. This time a mountain versus a valley. And the difference between the two is in this b function, it was positive. And in the numerator of this a function, you will notice that it is negative 2 right there. So that's what's flipping this thing over. Again, just for practice on domain and range, all reals, range, y is going to be less than or equal to 3, but greater than 0. Remember, I do not include the value of the horizontal asymptote, so that's why it doesn't say or equal to 0 there. I got to be above 0. Let's move on to a different type. What about when our degrees of the functions are the same? So now we see here we have a second degree function and a second degree function giving me that situation. And when this happened, we said we looked at the coefficients, the lead coefficients of each. So our y equal lead coefficient over lead coefficient makes negative 1 over 1 or 1. And this is my horizontal asymptote for this thing. Y equal 1. Verticals, x squared minus 4 equals 0. X squared equals 4. Now I get 2 vertical intercept or vertical asymptotes by setting the denominator equal to 0 plus or minus there. And x-intercepts, negative x squared equals 0, so x equals 0 is an x-intercept. So now we have all the players working together here on this one. So let's put everything in. So our horizontal asymptote is at 1. Vertical asymptote is at negative 2 and at positive 2. And I have an x-intercept of 0. So we're going to go ahead and put that x-intercept in there. Whoops, my horizontal asymptote should be at -1. Sorry about that. All right, so move my horizontal asymptote. Should have been -1, so to positive. There we go. All right, put our table values together for this one. I have a little more I need to test because I've got these areas left and right of my vertical asymptote. So let's say I'm going to put in, let's try a -8 in there. And how about right next to the vertical asymptote on the left-hand side of that first one? How about a -3? And then let's test a -1 and a 1, since that's in between my two vertical asymptotes. And then we'll test a 3 and an 8. All right, -8 in there. All right, in the top, up here, I have a negative of an x squared. So when I go to put my -8 in there, and I square it, I get -64. This negative is not a part of the base. It's not being squared, so be careful with those types of problems. If I wanted it to be squared, I would have included that in a parenthesis. So on the top, I get -64. On the bottom, I get a 64 minus a 60, or 64 minus 4, or 60. So I have a -64 over a 60, and that reduces to a -16 over 15. Just -1 point something there. -3 on the top gives me -9, and a -9 over a 9 minus a 4, or a 5, gives me -9 fifths. And I would, again, be changing these to decimals. That's -1.8 right there. -1 on the top, and -3. So now I get a 1/3. And when you put a 1 in, same thing, 1/3. Putting a 3 in, you get -9 on the top again over a 5. And I'm going to get -16 over 15 when I put the 8 in. All right, so we would change all those to decimals. We graph them. I get -8 and -1 and a little bit more. So I'm just sitting shy of our horizontal asymptote. -3, -1, and an 8, 1.8. Puts me right there. So I'm going to have a branch that's going to sweep as I go left to right on that problem. It's going to sweep along those asymptotes. In the middle, -1 and a 1/3, and 1 and a 1/3. And then over on the other side, 3, -1.8, and 8, -1 point something. Again, really close to that asymptote. And here's what it would look like. A little different shape than we've seen before. Now, domain and range on this one, again, might be worth having a little discussion about. So the domain is x cannot equal plus or minus 2, but it can be anything else. It's just not going to be the values of my vertical asymptotes. In terms of the range, I'm going to be, if I look at the below horizontal asymptote, I'm going to be less than -1. But I'm also going to be greater than or equal to 0. So we could say y is less than -1, and then union that with y is greater than or equal to 0. We can use interval notation and do IB interval notation, -infinity to -1, don't include it. Union with 0 to infinity. But that would be the range of that function. Then we get something a little different here. Got a difference of 2 squares in the top and the bottom in this case. So once again, the degree of the functions are the same. So that means for the horizontal asymptote, I'm able to use the leading coefficient over leading coefficient, which is 1 over 1, which is just 1. Vertical asymptote, x squared minus 4 equals 0. So x squared equals 4. So x is equal to plus or minus 2. And horizontal, x-intercepts, you would set x squared minus 9, a numerator equal to 0. And find out that I have plus or minus 3 for this one. All right, so let's go ahead and put all this in here. Asymptotes, y equal 1. Verticals, plus and minus 2. Horizontal, we got that. X-intercepts. X-intercepts are positive 3 and negative 3. So we're right there, and we are right there. Putting our table together here. I'm just going to use some of the same points I was doing before. Don't need to test negative 3 because I know I'm right there next to that asymptote. So I'm going to go ahead and test negative 1, and then 0, and then 1, and then an 8. All right, 64 minus 9 is 55 on the top. And then 64 minus 4 is 60, so 55 over 60. Again, I convert that to a decimal there. Negative 1 gives me 1 minus 9 is negative 8. Negative 8 minus 3 is 8/3. 0, I get 9/4. 1, I get my 8/3 again. And 8, I would again have 55 over 60, just less than 1. So here's what it would look like after I plotted all of those points. So you'll notice there's your 9/4, or where x is equal to 0 right there. And domain and range on this graph. Domain, x cannot equal plus or minus 2 again. And the range would have to say, this time we're going to be y is less than 1, and we're going to union that with y is greater than or equal to 9/4. All right, those were our two conditions where we were going to kind of have an emphasis on that for our class. We're going to just take a look at this next condition. This is where your degree of your numerator is bigger than the degree of your denominator. So you have an m greater than n, and this leads to what we call an oblique or a slant asymptote. So this is more of an FYI again. I'll show you how we would work through these problems, and then we'll wrap this thing up. Vertical asymptote, same old story. X plus 2 equals 0, so therefore x equals negative 2 is your vertical. The horizontal asymptote, since the degree of the numerator is bigger, there aren't any. X-intercepts, we'd set x squared minus 2x plus 1 equal to 0. And if we can factor that, x minus 1, x minus 1 is equal to 0. So x equal 1 is your sole x-intercept here. All right, and then let's take a look at the oblique asymptote. So because we have no horizontal asymptote, this is going to lead us to how do we find the oblique asymptote, or the slant asymptote. What we do is you're using long division, really, to come up with what the equation for your oblique asymptote is. So if we remember long division, we have x plus 2 as our divisor, and x squared minus 2x plus 1 as our dividend, and we do x squared plus 2x, and we would subtract that. We get negative 4x plus 1, and have x minus 4, and negative 4x minus 8. And we subtract that and get a remainder of 9. But the divisor without our remainder is really what we're looking for. That becomes the equation of our oblique asymptote. Y is equal to x minus 4. So let's put all of our asymptotes in here. We have a vertical at negative 2. There we are, negative 2. And we have this horizontal, or this oblique asymptote that goes from slope-intercept form, starts at negative 4, and has a slope of 1. And let's go ahead and go the other way with it. All right. So there would be our slant asymptote for that thing. Then, our points. This is where we may need to put in quite a few more points here, because we're going to get these weird shaped branches, although they're not really branches, but these weird shaped components to this particular rational function. I'm going to test, let's say, a negative 6 and a negative 3, and then a negative 1, and then perhaps a 0 and a 2, and then let's say a 5, and let's go 10. Let's see what's going on here. So we put all these values in. Negative 6 squared, 36. 36 plus 12, 48. 48 plus 1, 49 on the top. 49 over negative 4. Negative 3 in there, I get a 9. 9 plus 6 is 15, plus a 1 is a 16, and a 16 over a negative 1. Negative 16. Negative 1 in that, I get 1 plus 2 is 3. 3 plus 1 is 4 over 1. The 0 would give me a 1/2. 2 would give me 4 minus 4, which is 0. 0 plus 1 is 1. And then 1 over 4. 5 would give me 25 minus 10 is 15. 15 plus 1 is 16. And 16 over 7. 10 would give me 100 minus 20 is 80. And 80 plus 1 is 81 over 12. And I took all those points and I plotted them. I would get this. And my graph, I need to adjust my grid here so we can see it. So let's adjust our properties on this. Let's make our y values become a little smaller. Let's get down here, maybe we'll go to 20. There we go. And when I did that, I messed up my stuff here, so I'm going to have to adjust my scale a little bit. So this thing needs to rotate. I'll give it a 1-to-1 slope, and let's put it back where it should go, something like that. Not quite 1-to-1, maybe a little more slant to it. All right, so there would be that slant asymptote, a little better defined. In fact, I'm still off a little bit. I've adjusted my horizontal scale a little differently than my vertical. So there we go. That's what this thing would look like. A little different. And again, if I wanted to just peek again at one more. Vertical asymptote, x plus 2 equals 0, x equals negative 2. Horizontal asymptote doesn't exist. The x-intercepts x minus 3x plus 1. So I get x equals 3 or negative 1 are my x-intercepts. And then my oblique asymptote again would do a little long division. X squared minus 2x minus 3. And I get x squared plus 2x. Let's subtract that stuff. And get negative 4x minus 3. This one happens to have the same oblique asymptote equation, y equals x minus 4. I put in my values here before I draw on my asymptotes just to make sure I don't have the same problem that I did last time. We pick our x's, we find our y's. I'm going to, just for the sake of time here, adjust our properties to make these different. And then x minus 4, where's my line going? It's going from here along that route right there. And then we bring it back on this way. So there's your slanted asymptote of y equal x minus 4, and our vertical asymptote of y equal x minus 2. Now, in terms of domain and range for these functions, we would be having to try and find out where these, what we call local maximum and local minimums occur. And we're, again, not going to spend some time doing that, but there is a way we can come up with those values. So there's just what happens with the oblique asymptotes when the degree on the numerator is larger than the degree on the denominator. Again, that's more of an FYI.